Okay, so hello everyone, we are Team 9, and today we'll be introducing you to the COR-ASSIST, a temporary left ventricular assist device. Cardiogenic shock or severe heart failure has a disproportionate burden on the US healthcare system. Each year, there are 50,000 cases, and of these, 40 to 60% of patients will not survive, even if they're treated immediately. And these treatments come with a hefty price tag of $2.7 billion. It's been shown that temporary mechanical circulatory devices can help increase the survival rates in these patients. And this really contributed to its large and quickly growing market recently. The current most common device on market is the intra-aortic balloon pump. But this is a device from the 1960s, and it's really not a very effective pump. Additionally, poor positioning and usage in patients with arrhythmias can lead to very severe complications. The other common device on market is the Impella 2.5, and this comes with an increased price tag of $23,000 per procedure. Recent studies have also shown that it's associated with very high variability in clinical outcomes with higher odds of bleeding, kidney damage, and stroke. And this might be due to the stiffness and larger width of it, which has also caused it to have a more limited patient population. With these devices in mind, we come to the specifications for our own device. So first off, we wanted to make sure that it's affordable. So we want to make sure that the materials costs are below $500 in value. We also want to make sure that it's a very flexible and thin design to prevent complications, so around 3 to 3.3 millimeters when fully compressed. Additionally, we want to make sure that we match, or at least match, the flow rate of the Impella, which is 50% of the normal cardiac output, or 2.5 liters per minute. And then finally, we want to make sure that it's easily incorporated into the current workflows and would need minimal training. And now I'll pass it off to Francesca to talk a little bit more about our device.
Thank you. Our device, COR-ASSIST, enhances the IBP design. First starts with a typical intra-aortic balloon, which is the main component of the IBP, and it utilizes a guide wire for positioning. In order to increase the flow rate of the IBP, we designed a polyurethane sheath to surround a nickel titanium, also known as nitinol frame, to then encompass the balloon. The polyurethane sheath reaches into the left ventricle, providing direct support to the ventricle and therefore increasing the flow rate. The nickel titanium frame provides structure for a device and allows for it to expand once pushed out of a catheter due to its memory properties. In order to allow for proper flow in and out of the left ventricle, we included a leaflet one-way valve and exit ports. The one-way valve allows for blood to be pulled from the left ventricle without any flow back in, and the exit ports allow for blood to be pushed out into the aorta. And finally, since our device will be inserted through the femoral artery, it needs to be compressed and inserted into a catheter. Now I'll be discussing the positioning of our device. As I just mentioned, our device has to be inserted into a catheter to enter through the femoral artery. It then travels through the iliac artery and then results in the left ventricle and aorta. Once our device is in position, the catheter can then retract. And we know our device is in position once the one-way valve at the end of our sheath is reaching into the left ventricle. Next, the balloon pump is inserted through the same opening along a guide wire and is pushed up into the sheath of our device. Now I'll pass it off to Will to talk about the pumping of our device.
Thank you, Francesca. So now that everything is in position, the balloon is ready to start pumping blood. So when the balloon deflates, this creates negative pressure inside the sheath of our device, which pulls blood from the left ventricle through a one-way valve into the sheath of our device. And when the balloon later inflates, this positive pressure that's now inside the sheath pushes blood out of another one-way valve into the aorta, where the blood travels to the rest of the body. Note that as there are one-way valves between the left ventricle and the sheath of our device, all the blood is pushed into the aorta during inflation. This cyclical inflation-deflation pulls blood from the left ventricle and pushes it out into the aorta, thus supporting the cardiac output of our heart. Once our device is finished pumping, the catheter is then pushed over the device and the entire system is removed from the body. Now I'll talk a little bit about our progress this semester. So for our proof of concept device, which we created in October, this incorporated a wire lattice mesh design, and it was mainly used for us to validate the flow output of our device. And here is our proof of concept device. The wire mesh lattice is non-expandable and there's a loose fit over it. However, it allows us to show that our device can have sufficient flow, as we can see in the video here of our device pumping water through the one-way valves. In addition, with this proof of concept device, we also validated the pumping mechanism of our device and the design of our valves. And now I'll pass it off to Shawn to talk about our minimum viable product.
Thanks, Will. So for our MVP, we upgraded from the wire mesh by creating a nitinol frame and used this to conduct flow and expandability studies. So our MVP consisted of a polyurethane sheath on the outside that was thermally sealed, followed by a nitinol frame on the inside. At the inlet of the device, we created a leaflet one-way bicuspid valve to allow unidirectional flow into the device. And near the inlet, we also created an exit port with a single leaf membrane to allow unidirectional flow out of the device. And following the sheath and the frame, we inserted the balloon pump, which is outlined here in blue. So for the MVP, we used 2 iterations of the frames with varying mesh or cell sizes of 1.7 and 2 centimeters to assess the effect of varying cell sizes on the expandability of the device. So on the left, we could see the guides that were used to create the frames, and on the right, we could see the resulting frames. And so to measure expandability, we would compress the frames and allow them to expand at room temperature. And we found that a smaller cell size of 1.7 centimeters allowed for greater expandabilities or ability to revert back to its original size compared to a larger cell size of 2 centimeters. So focusing on this smaller cell size, we then assessed the effect of varying temperatures. And we found that more physiological conditions at 37 degrees Celsius resulted in a greater expandability compared to room temperature conditions. And lastly, to assess the flow of our device, we created a vertical testing system to mimic the left ventricle and the aorta of the heart. So the dyed fluid on the bottom would represent the blood of the left ventricle, and the clear fluid on top would represent the aorta. And so we could see that as our device pumps, it's able to draw fluid, the dyed fluid, from the left ventricle compartment and pump it out into the aorta compartment. Now I'll hand it off to Al to go over our final prototype.
Thank you very much, Shawn. So moving forward from the flow and expandability studies, we move forward to a more rigid frame for more robust testing, as well as improving our sheath manufacturing. And finally, we developed a pressurized testing system in order to quantify our results. So here on the left, you can see our new improved decreased seams in the sheath of our valve design. This decreases the amount of this decreases the chance for prolapsing, which is when the sheath itself unravels. And on the right is the rigid stent, which allows for more robust testing in the future. Here's our final prototype, the completed device, which has more polished sheath and as well as the IVP on the inside. And here's our final prototype pressurized testing system, which is a closed system that is more physiologically accurate. And it also resolves the device floating issue present in our previous vertical testing. It is also outfitted with a flow rate sensor, which is connected to an Arduino, allowing us to quantify our results. Here is a picture of the device within the testing chamber, and here's a video of it working. So as you can see, when the balloon deflates, the water rushes into the central testing chamber, and as it inflates, it is pushed outwards through the flow sensor back into the main chamber. And the testing results are shown below. So as we saw previously, when we pumped upwards to 70 pumps per minute, we were able to achieve a 2.5 liter per minute flow rate. And next, I'll pass it on to Kristina to talk about our future plans and next steps for COR-ASSIST.
Thank you, Alan. So far, we have submitted and filed a provisional patent for our device, and we want to complete the conversion of that provisional patent. Later, we also want to partner with the manufacturer to increase the quality of our sheath and frame design. And then finally, move on to animal testing to gather better qualitative data on the safety and efficacy in pigs. And lastly, we'd like to thank Dr. Howard Herman, our clinical advisor, for all the help that he's given us throughout this year and for the access to the hospital and the IBP for testing. Thank you for listening, and we'll be open to any questions.
Hi, yes. Can you speak a little bit more to the differentiation from current models and either how you validated or how you plan to validate the benefit of this device over existing models?
Yeah, so that's a really great question. For now, we have a bench test, as you saw before. And this is something that's common for the very early stages of using almost like a model circulatory system. And then later on, after the designs are created, they're moved into animal testing for further validation. So usually for that case, it's in swine, and it's around the same things with flow studies over a long period of time are conducted.
Great presentation. I understand the models that you've chosen and the ones that you're planning on. Have you been able to do any direct comparisons to competitors? Like, you're making, I think, two arguments with respect to your differentiation between this one and competing products. One is cost, the other one is efficacy, right? So do you have any preliminary data, or what do you think it would look like if you had preliminary data, if you compared it directly with the Impella?
Yeah, so compared directly with the Impella, right now the Impella is around 14 French, which is around 4 millimeters, and so ours, when it's compressed, can be around 3.3 millimeters in width. So this, it's almost around a millimeter in difference of width, so that would decrease the complication rates. But we'd also have to test that in animals and in humans to validate it. And then also, right now we're using, most of our data is through a very loose sheath, so there's a lot of inefficiencies, and even then we're still able to match and exceed the flow rate of the Impella, which is 2.5 liters per minute. And hopefully that answered your question.
Yes, it did.
Yeah, okay.
Hi. I don't quite remember the exact materials. No, I wrote it down. Can you talk a little bit about your material selection and what you considered were good properties, or what's kind of standard in other products?
Yeah, sure.
I can take that, yeah. We chose nitinol for our frame of our device because it's already FDA approved and it's used in stents, so there shouldn't be any biocompatibility issues. And it also has a memory property, so it can be compressed and revert to its original shape when it's in position. And the polyurethane, which is outside of the nitinol stent, that's actually the material that the IBPs currently are made out of. So with all that, they've all been used in humans for a very long time, so that's why we chose them, just to make sure there's no biocompatibility issues with any of our materials.